So we have the ripple carry adder circuit here, and we have it in ACL2 syntax, which is great because that means that we can now bring the power of the theorem prover to bear on this. So let's just check to see whether we have any reason to expect that this works. And here what we have is a little theory, okay? So we have A is a natural number, B is a natural number, and C is a bit. It's either 0 or 1, okay? So what we'll do is we'll take A and we'll convert it to a numeral, okay? We'll take B and convert that to a numeral, and we'll send that to a ripple carry adder. So we convert the numeral that corresponds to A, the numeral that corresponds to B, and the carry bit, and give that to our ripple carry adder, and take the result, and then we'll convert it back to a number. And what we get is actually equal to A plus B plus C. Okay, so that's what we want to be true, and we can actually test this, and it'll come up and do lots of random, natural numbers, and carry-in bits, and it won't find an error, right? Because this is actually a working program, and so there's no counterexamples, right? Now let's try to prove, right, that it actually is a working program, and the way that I went about this proof is like this. I decided to take the carries and kind of treat them separately. Okay, so the first thing I needed to worry about was what if the carry bit that's coming in is a 1? Okay, well if the carry bit is a 1, then actually I can just take whatever the result is when the carry bit is a 0, right, and add 1 to it. Okay, this proof actually goes through fairly nicely. It uses induction. Okay. And you should be able to prove this using induction. Okay, this is very similar to the proof that we did for things like the length of the union is the sum of the things and so on. Now I will give you just a hint to make life easier. Add this hypothesis that the length of A's is equal to the length of B's, and you just put that right here. Okay, it's just an extra hypothesis. It's not needed. You can prove it without it. But then you have to worry about all possible cases. What if the length of A's is smaller? What if the length of A's is bigger? That just complicates things. In a circuit, you would actually be adding 2 8-bit numbers, 2 32-bit numbers, 2 64-bit numbers, and so on. So it's actually a reasonable assumption to add. And if you do that, then actually the case analysis is much simpler. Okay. All right. So let's say that we have this. We now have this theorem proved. So we know what happens when the carry bit is equal to 1. And so now all I have to worry about is the case when the carry bit is equal to 0. Okay? And when the carry bit is equal to 0, what we can show is that if you add A's and B's, what you get is actually the sum of the A's and B's. And actually, again, it's easier if you simply assume that the A's and B's have the same length. Okay, so yeah, A's is a list of bits, B's is a list of bits. I add those and I convert that to a number, and I get whatever number I would get if I mean the sum of the numbers that I would get if I converted A's to a numeral. So it would be the number A, and B's to a numeral, so it's the number B. So yeah, that actually goes through the theorem prover. Okay, and then this is I guess a big moment where we say, well, let's just generalize that to any carry bit, either 0 or 1. And what we'll do is we'll prove this with cases. Okay, so this is a hint that we give to theorem prover. Like I said, often the theorem prover cannot prove things by itself. One of the ways that we help it is by proving lemmas that it can use. The other way that we help it is by actually interfering and giving an explicit hint, which is what we do here. We say, look, just think about these two cases. Suppose the carry bit is equal to 0. Suppose the carry bit is equal to 1. Okay, and of course there's a third case. What if it's something totally different? Well, if it's something totally different, then bit P of C takes care of it, right? Because we're assuming that it is a bit, so it has to be one of 0 or 1. Okay. Now, if the result is actually, the carry bit is equal to 0, then the previous theorem proves it because it said that was the case for when the carry bit was 0. Otherwise, then the lemma that we proved earlier comes into play because it's just 1 plus whatever happens when the carry bit is equal to 0. And so that works absolutely beautifully. Now, we've proved this, but notice what we did. But what we proved it was when A's was a list of bits and B's was a list of bits. What we actually gave the little theory was this more interesting theorem that said, what if A's, B's, and C's are just numbers, okay? And so now what happens? The reason I did that was because it actually helps to do it this way. This is a simpler proof. And what happens, the reason that it's simpler is because you see I'm adding A's and B's, just lists. Whereas in the theorem that I want, what I'm adding is numbers to bits, okay? So I would have to have some relationship about what do the numbers to bits look like for A minus 1, right? And quite frankly, the induction is just not as simple, okay? So it makes sense in cases like this to actually just do the proof in two parts. So here I'm using structural induction on lists, and that works perfectly for the full adder circuit. And it's only after that that I want to work with the numbers, okay? But actually, this is nothing. It's just a special case of the previous theorem, because the previous theorem says that this works for any sequence of bits, and now I'm trying to apply that for the specific sequence of bits that corresponds to the numbers A and B, right? So I tell it to do that. Again, I have to give a hint, okay? And my hint is this. Come up with an instance of a theorem that we just proved, bits to number adder, right? And when I talked about the bits A's, what I really mean is numbers to bits of A, right? So this is A's. And when I talk about B's, I really mean numbers to bit of B. So that's B's, okay? And go ahead and use that theorem, right? And you should be able to prove it very, very quickly, okay? Now, one complication, which is really just an ACL2 complication, so it's not something that I want you to spend a lot of time thinking about, okay? But one complication is that ACL2, when it's trying to use this instance of the theorem, has a lot of lemmas that it's already learned about numbers and adders and so on. So it'll actually try to apply those lemmas, and it'll get confused because it'll open things up, and then things won't look like what we want them to. So what we do is we say just disable all those lemmas. So for example, don't worry about bits to number adder, don't worry about bits to number to bits, and so on. Just trust me, look at it, and then you'll see that it's obvious. That's what we're telling ACL2. It doesn't have to do that much work, and that's the trick to actually making it succeed.